All right, good morning. So I sent out an email about the assignment due date being Monday, not today. And I'll have office hours this week right after the class today. And I know that some of you have other classes right after this class. So for them, Friday, that's tomorrow, we'll have an extra class, and I'll hang around for a little longer after the class. And moving forward, I'll have to find a time that works for everybody for office hours, because I might have to do 2 short things in a week or something like that. So, all right, and the extra, or the makeup class for the couple of classes we missed last week will be tomorrow in this room, 5 to 7 p.m. And I think there'll be 5 such things through the semester, looking at the calendar. And the calendar is posted, so please keep those times available for this class. Okay, so it was the end of the class on Tuesday. We were discussing a few things about kind of building up the ammunition of knowledge of quantum mechanics we need to do quantum transport, right? And I want to continue from that perspective today. And hopefully by the end of the class today, we start applying these rules, which are slightly different from the laws of classical mechanics and classical transport, and start seeing how, in general, one looks at transport of electrons in solids or in other kinds of materials, semiconductors, nanotubes, graphene, superconductors, and so on. So it's kind of a general formalism for it. That's what we're developing at this point, right? So, okay, so we had ended up with the, developing the basic notions of quantum mechanics takes quite a few other classes, but I think here the way we are going to do is accept some of the laws of quantum mechanics and start using it, and get familiar with how one applies them for the transport problem. Right? So one of the things we said was the Newton's laws or classical mechanics laws get modified in quantum mechanics, and the equation we need to solve to find any things of interest for in one dimension, for example, it looks something like this, is equal to energy. So that's the the time independent Schrödinger equation, and because the particle has a wave-like nature, because of the wave-particle duality, we are forced to deal with a wave function. We can't just say, well, here's the x and here's the momentum of the particle anymore, because they're not well defined, right? And therefore, I can't write that the energy is just from classical mechanics. We saw that you can write it as the kinetic plus potential energy, where both the kinetic and the potential energies are exactly known. So in classical mechanics, I can write the energy this way, but in quantum I can't, because x and p are not numbers anymore. Right? So that's the thing. X, because the location is not very precisely defined, x, and the momentum along the x direction, p sub x, let's call it p sub x. So if this was a point, where I could exactly define where the particle is and at what velocity it is doing transport, at what velocity and in which direction it's moving, then I'm good with classical mechanics. I can find its total energy. It's in some sort of a potential landscape, maybe in a parabolic potential, whichever way you look at it. And then, based on where you are in x, you can find your v of x, right? And you can find the total energy this way, right? So at what velocity it's moving. But in quantum mechanics, we said that because of the wave-particle duality, the particle's location is not very well defined. Maybe it's spread out a little bit. It's some sort of a wave packet. It's a little spread out this way. And similarly, there's delta x here. And similarly, in the momentum direction also, it's spread out a little bit. So there's a little blob here rather than a spot, right? Rather than a point. And that is delta px. And we also saw that for any wave, in fact, this is true. That is the uncertainty in that. Right? So I can make the particle very precise in the x direction, but then it'll spread out. It'll become more cylindrical in that direction. Or I can make the momentum very precise, in which case this will spread out. Right? So there's that sort of thing going on here with the uncertainty relation. Right? In fact, to be very precise, because of this spread, you can see that we cannot associate the location of a particle. We cannot mathematically represent the location of a particle by one number anymore, right? I mean, here I could say, well, it's 5 nanometers, but now I have to be like 5, little bit in 5, little bit in 5.1 nanometer, little bit in 5.2. So there's a little spread out, right? So there's a certain probability associated with it, as to, or haziness to that. Similarly, there's spread in the momentum, and therefore these are not numbers. In fact, to be very precise, these are matrices now. Both x and p are matrices. Right? And we will look at the matrix version a little bit later, but the algebraic version or mathematically algebraic version of a matrix, you can say it's a matrix and a function are kind of similar. So what we can say is for differential equations, a matrix is same as an operator. It's not a number anymore, but it's an operator. Just like, and one of the things that happens, which you can think of an operator, x being an operator and momentum being an operator, equivalent in many ways to a matrix. And I think you know that a matrix, one of the defining properties is if I take A times B, it may not be necessarily equal to B times A. It fails to commute, right, with each other. Just like, in classical mechanics, x times px minus px times x will always be equal to 0 because these are numbers, right? Be it complex numbers, even if it's the complex numbers, that is always 0, so they commute. Whereas the most fundamental quantities of transport or mechanics of a particle, which is the location and momentum that we build all our understanding around, suddenly they're not numbers anymore. They're matrices or operators. And if we think of it as operator instead of a matrix, then I think you know this. So we put a hat typically around it, right? And we say that this is not equal to 0. If this was 0, you will be in the realm of classical mechanics, but this is not 0 anymore. In fact, this is a very precise number, right? And that's the heart of quantum mechanics, actually. And this is exactly equal to I times h bar, or Planck's constant, right? The commutator or these two variables have to precisely satisfy this, and that's basically all of quantum mechanics built on this this is the bedrock of quantum mechanics, right? So if you put that to 0, you go back to classical mechanics, okay? And we write this as sometimes x is understood without the hat, momentum sometimes understood, so we can write it, or this mathematical operation of taking a quantity times another quantity minus the two swapped in positions, that we will call as the commutator. This is the symbol for it, brackets, is equal to IH bar, right? Okay. So that's the major change from classical mechanics. And what we want to do now is write down the relation for, so this is the energy, and if you want to track the dynamics of the particle in classical mechanics again, the dynamics of a particle is a path in the phase space, right? It would go from, say, point A to point B, and the law of motion for that dynamics of a particle, or the time, the change in time is that the force is mass times acceleration, right? This is the Newton's law, And we want to find out what is the quantum law of dynamics of the particle now, right? That's given by the time-dependent Schrödinger equation, right? That's the equivalent of the second law of, second Newton's law, right? Which is force is mass times acceleration, right? And what's the first law of, mechanics, or first Newton's law, right? So, yeah.
Everybody is in a state of inertia, it's force acts.
Right, so it's the law of inertia, right, that unless a force acts on our body, it's going to either stay at rest or at a state of constant velocity, right? So that's the first law of motion, of transport in classical mechanics. We will have equivalent first law in quantum mechanics too, and that's what's going to define what are called stationary states, meaning if you don't have any forces acting on a particle, it will stay in an eigenstate, So that's the equivalent law of transport, quantum transport. Okay, so again, as you can see in quantum mechanics, what will happen is you will have some sort of a force or a, potential acting on this object, which is a wave particle, has a wave particle duality, and it's going to kind of drag along this cloud with it. And maybe by the time you reach here, it's maybe elongated a little bit that way, and it's going to deform a little bit. Depends, upon the nature of the force, right? So is in fact, the time-dependent Schrödinger equation is a law of diffusion of this sort of, thing that's the wave particle aspect of it that's dragged along by along with the particle itself. So the time-dependent Schrödinger equation is IH bar, d psi over dt, right? Rate of change of the wave function is equal to this, which we are going to, this quantity, right? Which we are calling now, we're going to call this as the Hamiltonian. This comes again from classical mechanics because Newton's laws of motion. For example, this law can be derived from more constitutive, more basic equations called the Hamiltonian equations, right? And don't have to know all that at this point, but that's the so we're calling that the Hamiltonian. And this is now our v of x acting on psi. That's basically the full equation, time-dependent Schrödinger equation now, right? So those are the two probably the most important laws of quantum mechanics we're going to use in this course. We're going to look at it in many formats. In fact, hopefully by the end of the class today, we are going to already look at these equations in slightly different formats. But essentially, the ideas are start out from here. Okay, so you have seen this earlier in some courses. Okay, so we're going to piece apart of quite a few things here, and hopefully that may add a few new notions of what this actually means and such things, right? So that's the time-dependent Schrödinger equation, and that basically the idea of any transport problem is now if you're looking at transport of electrons or in vacuum or in solid, you find out basically the idea is this is what you need to solve, right? And by solving this, you can find out what is the wave function of the electron at any point in space and at any time t. You can find that out. Right? For that, what do you need to know? I need to know what is my potential, right? What is the potential that the electron experiences, right? So, the force does not directly enter here. What enters is the energy or the potential, right? So that's what enters here, and then I have to solve this, partial differential equation, and if you can solve it and find out what is psi of r comma t, now you can act on the wave function and say that, well, at time say 20 nanoseconds, what is the momentum? So you come in with the momentum operator, act on it, you can recover the momentum, and so on, and that's the game, right? And then what's the energy? You act with the Hamiltonian operator on it and find the energy, and so on, right? Angular momentum, any physical variable, you operate, you if you know the wave function, you know everything now, right? So that's kind of the game. Many times it's impossible to calculate the wave function exactly, and that's why we need to develop quite a few approximation techniques and things like that to get to the solution. But at least conceptually, it should be clear this is what we are doing, really, because it's saying that Newton's laws have been modified. Here's a new law, solve it, and you get the wave function, and then you're done. You can. So if you have, instead of 1 electron, if you have 1,000 electrons or 10 to the power 22 electrons, then there's an index I. For each electron, you can track it, right? And what's the wave function of each of them? So that's the idea, right? And sum them all over to get the total picture. So any questions here? All right. So what we are going to do is first look at the time-dependent Schrödinger equation a little bit now, and from here derive a equation. Okay. Derive a few things, which again we'll use quite extensively in this course, and specifically we derive a relation for the current density, quantum mechanical current density, and things like that. But first, let's look at this wave function and say that. So the idea of this equation is any psi that you can find that satisfies this relation for a given potential is an allowed solution. Any psi that you can find. If you can find 3 different psis, 3 different wave functions, you can take some undetermined coefficient times the first one plus some other coefficient times the second one. You can superpose them, and that is also a solution. So all of these are allowed states for the particle. And which ones do they actually occupy? Which ones do they, that really depends on a few things which we will, highlight. But out of all this, kind of infinite number of allowed states. Let's look at a restricted number of sets of states where, so instead of writing R, let me just again use one dimension x, comma t. This is a wave function in both space and time, right? Space and time. So we can try to find a restricted set of solutions where I can say separate the space and the time variables from each other. It's a restricted set, right? Sometimes you can't separate them, right? Does that make sense? So let's say, for example, if my wave function was e to the power minus, x minus a t whole squared over some x naught squared, right? So you can see I can't separate that thing into something that has only x and something that has only t. Right? I can't separate that one. But if I had, e to the power I kx minus omega t, sure, you can separate it, right? You can write it as e to the power I kx, e to the power minus I omega t. So that's separable, right? Yeah.
Would that also mean that you wouldn't be able to normalize it?
You can normalize it. You can normalize it, meaning what I'm saying is at this point we are looking at a restricted set of solutions. You can always normalize it, meaning if I choose this, you can definitely normalize it. It's a Gaussian, you can definitely normalize it. But I'm saying if I choose a Gaussian, I cannot separate it like this. And I've not said anything physical. All I'm saying is I'm only going to look at those states and explore what are their properties. And what we're going to discover now is for those states which are separable, they lead to the eigenstates of the system. So whereas this one is not going to be an eigenstate at this point. So that's what I want to kind of say.
But the probability is always going to be independent of time, right?
Only for the eigenstates. Okay. Yeah, only for the eigenstates. Exactly right. And that's the stationary state. So we're going there right now. So, yeah. Okay, so we're going to look at this restricted set, and then so we take this and plug it in here, okay, and see what is it leading me to. One thing to notice is this Hamiltonian is only acting on the space variable. So it's doing something or operating on the x, not on the time. Right? This d by dx multiply with x, but there's no time inside here. This one. Right? Later on, when we are going to look at things like a phonon or electron interacting with something that is really, vibrating in time or changing in time, then this one has to be a little careful with the approach we are taking here. But at this point, we are saying it's a time-independent potential. The electron is going through a crystal where the atoms are probably stay put, they don't vibrate or something like that, they're frozen, or it's going in vacuum, in which case, indeed, there is no time-dependent phenomena. So this part only operates, this part only operates on x part, on the space part, right? Whereas the left-hand side, all this stuff operates only on the time part. Right? So let's write that down. So we write I h bar, and d by dt of the whole thing is only going to operate on the big T part, and dot here means the time derivative. Okay? So it's one time derivative, and it's going to leave the spatial part alone. It's not going to mess with that one, right? So that's the left-hand side. And what's the right-hand side? On the right-hand side, the time part is left alone. It doesn't, this Hamiltonian doesn't act on it. So you can pull that out. T of time times, Hamiltonian acts on the spatially dependent part chi. Right? Okay, makes sense. So that's what time-dependent Schrödinger equation says should happen to this restricted set of wave functions. And now I can rearrange it a little bit and write it as T dot over T. Just bring that over here, take that over there. You get Hamiltonian acting on the spatially dependent part over just the spatially dependent part. Right? So that's here. Meaning, what you can see what we did here was took all the time-dependent part here. So this is changing with time, is a function of time, but not a function of space. There's no space dependence left here on this side, right? This part, things are changing in space, but not dependent on time at all, right? This part. And what Schrödinger equation is saying is that for this restricted set of wave function solutions, something that is clearly changing with time but has no notion of where it is in space, and something that is changing in space but has no notion of what time it is, must be exactly equal, right? At all points of time and at all points in space, right? So that can only be true when both of them are equal to a constant, right? Both of them are equal to something that changes neither in space nor in time, right? Because you can sit at one point and in time and change space, and your wave function can change a lot and all that. It's not possible to have a time invariant thing and a spatial invariant thing simultaneously unless both of them are equal to one number or one constant. Does that make sense, this argument, right? And what is that constant? In terms of units, you can see right away what that constant should be. It should have units of what? Yeah, so you can look at your time. So it should have units of energy, right? Energy. And okay, so I'll just write it right away here. It's a unit of energy, or joules, or electron volts. It's a physical quantity. And so from here you get two equations that the time-dependent part, or you can write it down that the partial, okay. Right, I just rewrote it by taking it to the right side and flipped the I sign of I. And so from here you get that the time-dependent part must be equal to whatever it is at time, say 0, or any reference point you want to choose, and it should change with time. Yeah. Yeah. Oh, yeah, you're right. Sorry. Yeah, thank you. Right. So from here you get that the time-dependent part of the wave function should evolve with time in this fashion, and energy over Planck's constant has units of frequency or circular frequency. You can call it omega. It's a circular frequency in radians per second. So this state effectively, the time-dependent part of it rotates, or if you could think of it as a vector, it's rotating at a frequency of circular frequency of omega, in that way. Okay, so that's the time evolution part of, just to be clear, of this restricted set of solutions, not all, but only this restricted set of solutions, right? All right? And similarly, from the spatially dependent part, you get that the Hamiltonian acting on chi should give you E times chi, where this is your spatially dependent part. And this is really the same as this equation. So you can recover the time-independent Schrödinger from the time-dependent part. That's physically it's the same. So you can operate on the Hamiltonian, on a wave function, and clearly the time part is gone here because in fact for this restricted set of solutions, there is a time part, but it cancels from both sides because it's the same on both sides. It's something like this, right? It cancels out, and so this is a set of solutions again. As you can imagine, you may or may not have a continuous set of energies. If you have a free electron, you have a continuous set of energies. If you have a particle in a box, it's a discrete set of energies. These energies are completely determined by your V of x, or the potential of the Hamiltonian, right? So this determines the spectrum of energies here. What energies are allowed, what are not allowed. That's determined by the potential that the particle sees, right? But regardless, once we combine the two, the total wave function now looks as whatever is this chi, the function of space times some constant times e to the power minus I e over h bar t. Right? That's the full-blown solution now for this restricted set for which you can do the separation of variables. And that's clearly a set of solutions of the time-dependent Schrödinger equation, right? Okay. Now, just like if you look at an electromagnetic wave, if you have an electric field and a magnetic field, right, and the electromagnetic wave is propagating and you have oscillating and all that, right? Magnetic field oscillates, electric field oscillates. The energy of the electromagnetic wave goes as E squared plus half some constants here plus B squared, let's say, right? Something like that, E squared and B squared. So energy, or the intensity or the density of photons, if you might, or in an electromagnetic wave, depends on the square of the field, square of the electric field, square of the magnetic field. In a very similar way, in quantum mechanics, which is Max Born came up with the interpretation that the probability density of finding a particle, or the intensity of finding a particle, is related to the square of the wave function, not the wave function. Wave function is the amplitude, right? And it has a phase, and you take absolute value squared, you get the intensity. And it's very much analogous to the intensity content or photon content of electromagnetic waves. So mod psi squared is the probability, right, of finding a particle at point x at time t. You can see right away for this restricted set of solutions, if you take mod psi squared, this term just goes away, right? E to the power I omega t goes away because absolute value of that e to the power I omega t lies on a unit circle in the complex space where this is real, imaginary, right? It's never zero. E to the power I omega t can never be zero, right? Right, it cannot be here. It's always on the circle, right? So it's never fully zero. But the absolute value is 1. So what you get is that So what we're trying to say is this is independent of time. Mod psi squared is independent of time. And so this set of solutions where you can separate the variables have a uniquely defined energies, as given by this, and these are not changing in time. The state of the wave function, the probability density of the wave function is not changing with time either. And so this set of solutions are called stationary states, right? The allowed energies of these are called the eigenvalues, or energies are called eigenvalues. or eigenenergies for that matter. And this is a special set of solution because as you can imagine, if you want to know the dynamics, it is always useful to build it around something that is not changing with time first. That's your basis. That's what it's not changing with time. And then on top of it, you say, well, I'm going to act on this sort of particle, on this particle with a force, and it will hop between one eigenvalue to the other, and that's your transport process typically. But the one that is not changing at all, the basis is the stationary state. For a stationary state, after you're done solving your entire quantum mechanics problem, what you have is a set of energies. Given the potential, you can have a set of energies, set of wave functions. You know the rate at which each energy can be, state is evolving with time, but the probability is stationary. It's not changing with time, right? So these are stationary, and that's your. This set of solutions is equivalent to your Newton's first law. This is the state that stays if there is no external force acting on it. If you put a particle in a particular state, say E1 or E2, so let's say you have solved your potential problem. Maybe it's a harmonic oscillator problem, and you have this set of energies, E1, E2, E3, or a hydrogen atom, ground state, excited state. Let's say you have put an electron in this state, E2. It will have its own energy here. It will have its own wave function, right? The wave function, for maybe a ground state is like that, excited state is like that. So the electron will have a wave function, or the chi will be something like this. Okay? If it's sitting in this state, the energy would be whatever it is here, E2, so it will have a certain frequency of rotation, right? And if I put it there and I leave this harmonic oscillator alone, that electron is actually never going to jump to another state. It's going to just stay there. The probability of finding it at any point of time in the future, mod psi squared, is exactly the same as what it is now, right? It's not changing with time. Does that make sense? I mean, this is a very important concept, and this way, and this is equivalent to your first law that a particle at rest will stay at rest, or uniform motion. This is the equivalent part of that law of classical mechanics. Okay, so is that yeah, question?
Does T0 have a physical meaning?
Say that again, T0?
Yeah, does it have a physical meaning?
Oh, yeah, yes. So, T0 is, so you can actually normalize. One way to look at it is T0 is e to the power some constant angle. So it's a phase, initial phase of the particle, if you want to think of it that way. But if you look at the probability of it, you can, typically what's done is you can normalize this part, in which case T0 is actually 1. But if you normalize, with this phase, right. So you can think of it as phase. It has a physical meaning, but it's it can be thought of as an initial phase of the system. That's probably the closest to the physical meaning it can get. Yeah.
Am I thinking this wrong? Is stationary states referring to bound states that wouldn't even change with perturbations and things that you would add to the Hamiltonian? Well?
That's a good question. So actually, this is a very general result. It doesn't have to be a bound state at all. It can be a completely free electron moving with extremely high velocity in a certain direction, in which case, it will have a certain energy. It will be high kinetic energy, and it will stay in that state unless there is anything else that's going to perturb it. So anytime I change the initial conditions, meaning, so I have a certain potential for which this energy has been found. If I perturb it, if I put a well or a barrier in the path of the electron, then things are going to change, right? And it won't remain stationary anymore. It will scatter, it will mix states and all that. That's what leads to transport. But as long as, if I look at, say, a silicon crystal, and I'm looking at electrons and that are moving in the silicon crystal or any other crystal like that, the potential of all the atoms of the crystal, you take them and you solve this and you find the energies, and that's your band structure of the solid, right? And in that band structure, let's say, I have something like this, E versus K, And I found, well, that's a K state, that's another K state, this is my spectrum of eigenvalues. And say the electron is here, and it has a certain energy, and you put it there. What time-dependent Schrödinger equation is telling you is it's going to stay there forever. It's not going to go down or go up. No, it's not going to do that. And you know that's not quite right? Because if you put it here, it's going to, relax down to the bottom of the band. And that's because there's phonons. We haven't even introduced that to the problem. That's a perturbation. Is that what you're asking? Yeah. So it will stay, in a state which may have very high energy, may not be the ground state. It can be an excited state, but it'll stay there. It's a stationary state, even though it's not the ground state. Harmonic oscillator, you put it here, it'll stay there. Now, what are the potential ways it can relax down to the bottom, or a hydrogen atom for that matter, right? Hydrogen atom has, say, n is equal to 1 and n is equal to 2 states. If you put an electron here, physically it doesn't stay there. It's going to go down. How does it relax? What does it do to relax its energy? It emits a photon, light, right? So that means it's coupled to the electromagnetic, spectrum, or the, electromagnetic, the vacuum itself has ground states of electromagnetic. It can contain photons, right? What you can do is you can actually forbid it from doing it. You can put it in a cavity in which, that exact energy that's going to come out is not allowed. It's filtered out. There's a notch in that. It doesn't allow that mode. In which case, this electron is actually going to stay there for a very long time. It cannot relax. You can inhibit the spontaneous emission process if you want to, in the same way, right? So.
But you're saying if it's out of phonon mode.
Right. So if the entire energy the electron sees is that of the proton here, and you do not have the electromagnetic wave in your potential term, the electromagnetic spectrum, then it cannot relax. But the moment you put in the electromagnetic wave, that's how you allow it to relax, to couple to another mode, or be it phonons or photons or whatever be it. Typically, it's going to relax by going into vibrational modes like phonons or photons, right? We are going to talk about phonons a great deal more than the photons in this course, at least. So, yeah.
So just a question to clarify. So for an isolated hydrogen atom, if we just have the potential from a proton, then it should be a pure stationary state, and it should have no way of relaxing.
Absolutely.
So how does the fact that there is the possibility of emitting a photon, how is that represented in the potential energy term, the fact that it can interact with the vacuum?
Right. The potential energy term for the hydrogen atom with the proton itself is just minus e squared by 4 pi epsilon r, right? But if you add in the electromagnetic waves potential, if you add in the coupling of the electron to the electromagnetic spectrum, right? So typically, not typically, the electromagnetic spectrum has its own, so to say, its own Schrödinger equation. Okay, so just like we have H psi is E psi, here electromagnetic spectrum has its has its own set of eigenvalues allowed, right? And that's given by some photon energy times number of photons plus half. It's a harmonic oscillator picture. So what you do is you add in this term to this term, right? And we are going to actually look at some aspects of it, especially the phonon part of it. It's exactly the same picture. So we add the Coulomb potential plus the wave, all the allowed energies of the mode it's coupling to, be it phonons or be it photons. And you solve this whole thing again, right, together. Because if you don't allow the electromagnetic spectrum or the phonon spectrum, there is no way it can relax, right? So it has to enter into the Schrödinger equation, and the way it enters is through this potential energy. And you write down, you quantize your electromagnetic wave or the phonon spectrum, and it's basically you sum it over all potential modes, right? And then you add it to this, and then you can deal with all these perturbations or any changes like that, spontaneous emission, stimulated emission, all that stuff. Yeah.
But in that case, your wave function wouldn't be expressed in reciprocal space, would it?
Yeah.
It would be in real space.
So all right. So it will for the exact. There are two ways to solve the problem. You can introduce these quantities, either light wave or phonon waves, and you try to solve the entire problem. Now that's hard, meaning to solve the problem as a completely new Schrödinger equation without taking advantage of the stationary states and all that of the uncoupled situation. Right? The other approach is perturbation approach, where you say that the photon or the phonon energy term is much smaller than the energies that the electron is seeing due to the proton or the nucleus and all that. So that's a perturbative approach. We're going to do both. We're going to do the perturbative approach first. The problem is even the exact solution of one electron in a hydrogen atom interacting with the free vacuum state of electromagnetic waves that's quantum electrodynamics is actually an unsolved problem even today. Exactly. If you want to solve it exactly, there are approximations by which you can solve it, but there's no exact solution. But you can write states that are. So what we are asking is, are there stationary states of this coupled situation, right? So can I write down stationary states? You can write something with certain approximations, but the exact solution is still missing. So that's what I'm trying to say at this point. We will see a few examples of it later on. All right. Okay, so now that may seem too abstract, but really we are going to start applying it and see some real. We'll calculate numbers and see how far of an approximation it is and such things. So, but this is an important thing because at least a large part of the course will be based on this idea that whatever is perturbation we apply is relatively small compared to these huge potentials the electron sees inside a crystal due to the nuclei and due to the other atoms and other things like that. So that's going to be the dominant one, and we are going to add up a perturbation, and we'll see order of magnitude. This will be maybe the crystal potential maybe 6 or 7 orders of magnitude stronger than some other thing we are applying. So we'll apply perturbative approach for that, for transport for those things. Okay, so yeah. Okay, so now what we'll do now is start from here, and I want to kind of make sure that we all right. So okay, we talked about how this is equivalent now to the to the Schrödinger equation, and we talked a little bit about this part, that probability density of stationary states. Remember, the stationary states are where this is separable and it gives you these eigenvalues. Just to be very clear, these are not the only allowed states. These are not the only allowed states. You can have a lot of states where you can't separate them, right? But the beauty of an equation like this, at least mathematically, it's you are guaranteed that every other solution you can ever find, you can ever cook up, can be written as a linear superposition of the stationary states. So it's a complete set. Okay? Does that make sense? I mean, any other equation you can cook up, any other wave function you can cook up, can be written as a linear superposition of this set of stationary states. Even the inseparable ones, like the Gaussian we talked about, even those can be written as a superposition of this.
So just like the Fourier series.
Exactly, and that's guaranteed by the Fourier series, pretty much. This is a complete set of solutions, but then you have to include all the possibles and all the possible solutions here. And for any physical system, what makes things a little difficult is it's always an infinite set. It's not a finite set. And that's called the Hilbert set in Hilbert space in quantum mechanics. So essentially, this is an infinite set, but for most applications, we will get away with 1, 2, 3 states. So, it's like a 3x3 matrix or something, 4x4 matrix. Most of our analysis will be on 2x2s, and you can develop great make great advances in understanding by just looking at 2 by 2, meaning 2-state systems. So we'll look at that in great detail. But in general, even this free electron, even the free electron with no potential whatsoever is an infinite set of solutions, because we have already said that the energies of a free electron is the allowed energies are h squared, k squared, 2m, and k is continuous, so all k's are allowed, right? So that's already an infinite set. Okay, just to get a physical feel for it, if I sketch the energies of a free electron, I can have energy there or there. Which one will have it's a simple question, but which one will have a larger angular frequency, omega? Right. So remember omega, so I'm saying that the wave function of this state is evolving as, what's the free electron wave function? Maybe you can tell me, if it's just a free electron, this is h squared, k squared by 2m, right? So what are the wave functions? This is something you should know, right? It's the bedrock of most stuff we'll do. So. Yeah, right. So the spatially dependent part, which is this chi, is just a plain wave, right? E to the power ikx. That you can get by writing, this is 0 for the free electron, right? And you solve it, your size e to the power, or this chi term, the time independent part is just some constant times e to the power ikx, right? That's your time independent part, right? And the time dependent part, I'm going to, again, you can see you are asking about the coefficient for the time part. You can absorb it in this a, it's just a number, right? You can just write it as e to the power minus I times e over h bar t, where this e is not any e, right? It's a very particular energy. Which energy is it? It's that energy that is tied to this k, right? Every k has a unique energy associated with it, or every k has exactly one energy in this problem, just one, right? So it's that energy. It's not any energy, but it's that energy, right? So in this particular problem, as you can see, it will look like e to the power minus I, h squared, k squared by twice mass. So there'll be 1h, and then this. You can see how it looks in time, right? And how. So clearly, as you increase the k, this energy over h bar, which is omega of k, is h bar k square over m, right? Is that correct, what I did? Yeah. 2m, sorry. Right? So the circular frequency is increasing at square of k, right? So it's, if you think of it as a vector, this thing is kind of, rotating slowly, and this vector is going much faster, if you think of it that way. Okay, so yeah. So this set of space is sometimes called a vector space, and it's an infinite space. It's called a Hilbert space, in a collection of all these vectors that are kind of spinning in time, if you think of it that way. That's one abstract way of thinking about this problem too. Okay, now the moment you put it inside a solid, or if you have a particle in a box, already you have a finite set instead of an infinite. Let me say, so if you don't have a finite set, you have a discrete set. It's still infinite, but it's discrete. Right? And then if you put it inside a box or in a harmonic oscillator, you increase the discreteness and things like that. But regardless, this story remains the same. So you have individual states. Each state has associated with it a certain wave function, which has a spatially dependent part and a time dependent part. If you come to this place from chemistry, these individual states will be called orbitals. That's another word for it, orbitals. It's an individual orbital. It could be, for a hydrogen atom, this could be a s state, this could be a p state, or things like that. These are orbitals. It's the same thing, really. They have different wave functions, symmetric, antisymmetric, and all that, right? And okay, so is that clear? Yeah, that's a question.
So the spatial part obviously affects the probability distribution. So how can we see the time part? I can see that it's there.
Yeah. It's a very good point, yeah. So you can only see the difference of two. You can only see the difference of, omega 1 minus omega 2 by a transition. Finding the time part of one state by itself, as you can see, you will be, if it's a stationary state, you can't do it, because it will be, observable is mod psi square, and it goes away. So it's the differences that you can see, right? And from there you can, it's all as a result, it's a relative thing now, right? So you can find out from there, right? Right. So even for the hydrogen atom, what you can see is all the lines which are omega, E2 minus E1, E3 minus E1, right? But you can build a theory says that where are you? Are you in the first state or ground state? And you can associate it. Okay. All right. So now one of the things is we want to make a connection from here to transport from individual states or individual orbitals to the transport problem. And the transport problem is formulated again in analogy to classical mechanics. And the classical mechanics analogy that we are going to draw, let's start with, I can erase this part. Right. So the classical mechanics analogy is, I think this is the way I'm going to describe it is really, to me at least, worth repeating, and maybe we'll look at it again sometime later. In classical mechanics, the way you do transport of particles is the basic idea is called the continuity equation. Meaning I have a certain number of particles here in space. I have a certain number of particles, and let's say my whole world is this little space here, and I don't know what's going on outside, but I can count, how many particles are here, and if I find, 5 seconds later or 5 nanoseconds later, I have a lot more particles. I know there was a transport of particles from my outside world into my world, right? So this is the continuity equation or conservation of particles. That's what it depends on. So the idea is if I have a certain number of particles here and some particles entered this point from outside, then I know that the number of particles has changed, and the rate of change of the number of particles here is because of a flux of particles that came from outside. And basically transport problem is you're tracking these transport, the transport of these particles, right? At least intuitively, that's very clear, right? And so to understand, to mathematically quantify transport, we say the particles came in through a current of particles. Current is, sometimes called a flux of particles, number of particles. It could be a charge current, heat current, spin current, just a particle current if it's just neutrons, which has, or something, or water molecules, whatever be it, right? So it's a current which has, very similar units as the. So for example, current density we talked about N times V, right? Charge times electron density times velocity. In general, the current, you can write it as particle number times the velocity of particles. That's the flux. And what it drags with it could be charge, could be heat, whatever be it, energy, right? So I'm just writing it in a general notion. This is the flux of particles. And what I'm saying is the rate of change of particles here, I think you can see, if this is a volume density, let's say volume density, then it has units of 1 over meter cube or centimeter cube, right? Let's see, centimeter cube, volume density, right? And this is because of particles that came in from outside. It's clearly related to the flux, right, or of particles J. But then you can see that if particles were going out, it will have some notion of a divergence of particles, or divergence of a flux if they're coming in. it also has a unit of divergence or convergence, if you might, and that's negative of the divergence. Let me just write it down, and I hope you can see. So mathematically, this is how it looks. It's dependent on the rate of change of the current. Rate of change of current. If there's a uniform current flowing in space, in X, the J is uniform, flux is uniform. If I'm sitting here, my particle number is never going to change. It's going to stay the same because same number of particles coming in, same number going out, right? But if it changes, then I have a buildup of particles or I have a decay of particles, and that's what this relation is saying. The rate of change of number of particles is related to the derivative, spatial derivative of the current. No quantum mechanics at all. This is the law by which you design pipe flow of air, in heating in buildings or sewage system is the same equation. Right? This is, rate of change of particle density is divergence of the current density or flux density. Now, you may have situations in semiconductors or in some, let's say in very high energy physics where you accelerated a particle so fast it just transformed into light, it just, so all that. In which case you are either losing particles. If your particle number is not conserved, then you have a couple of other terms here, and what they're written as you could be generating some particles or you could be recombining some particles. You could be losing some, right? So this is those of you have done semiconductor devices, you might say this is the continuity equation in any semiconductor device, for example. But that's a very general relation too. Generation or recombination can also occur. We are going to look at mostly condensed matter phenomena where we are not going to lose electrons. Their velocities are kind of not as fast as speed of light, and it's so if I have 10 to the power 23% electrons in a solid, it'll stay there. It won't change much, right? We won't be losing electrons. If at all, we'll be losing electron to the contacts, and to the metal, right? But they're not going to vanish forever. So we're going to neglect this for now. Later on, we'll bring it back where it's necessary. But at this point, we're going to neglect that. Okay. So that's the classical notion of this is the continuity equation, and that defines what we are going to use as a central thing in this course as the current, and a flux. You can think of it interchangeably. If I multiply it by the electron charge, it's the charge current, and electron spin is the spin current, and so on. Right? Is that clear? Any questions here? Okay. All right. So now what we want to find then is the quantum mechanical analog of this, given the fact that let's say I have done the hard part of I've located let's say my silicon crystal. I have found out what is my potential. I've solved my time independent Schrödinger equation. I know all the eigenvalues. I know the band structure of the solid and all that. Right? I know all the orbitals, all the energies. And now we're saying that I'm going to now I'm asking the question: what is the current flowing inside the crystal due to electrons? Let's say, or charge current, right? That's the question we're asking at this point. Now, why it's flowing is another story. We're going to come to that at some point. But let's say all the states, how are they occupied inside the band structure. Maybe this is occupied, this is occupied, this is unoccupied, this is unoccupied. All that, right? And then what is the current? So that's the question we're asking at this point. And we're going to write down an equation. And the equation we'll end up with is that J is the quantum mechanical current density is related to the wave function. Remember, that's where all the information lies. And it's given by the wave function, complex conjugate grade. Let's write it in a slightly different way. It's going to be 1 over twice the mass of, we are going to talk mainly about electrons. So it's the mass, free electron mass, times the momentum operator acting on psi, minus psi, momentum operator acting on psi star. So that's our current quantum mechanical expression for the current flux or the current density. Right? So where is it? Somewhere out here. Let me just bring that up. So this is also derived in your in the first set of notes, and I think those who have taken solid state or other things might have seen, or quantum might have seen this too. But that's the relation. The current flux is given by, if you take the wave function, use momentum operator on it, take psi star, and then you kind of flip the two around, take psi star first, momentum operator. That's what's going to give you the quantum mechanical current density. Now, just to be clear, I'm using word current and flux interchangeably at this point. I mean, so it's the same thing. The current is just whatever current you are interested in. Charge times this will be the charge current density. You'll get amps per centimeter square. Spin times this, you'll get what angular momentum, or spin angular momentum per, all that sort of thing. So yeah, there's a question.
The problem with like semiconductors.
Yeah.
Does that M become the effective mass? Or is that always just
No, in this form, it is always the free electron mass, whatever particle we're talking about. How it becomes effective mass, we're going to look at that later. So, but at this, the way it's written here. All right. So if you choose to use, the full-blown wave function, this must be the free electron mass. If you use what's called the effective mass wave function, then this must be the effective mass. So that's a slight difference here. Okay? But at this point, we are not making that distinction. We're saying it's a general result. You know what? I don't think I'll try to derive this at this point because it's done in the. But the idea is very straightforward, really. You take because you already know that what we are trying to do here is find the quantum analog of the classical continuity equation. And the number of particles in quantum mechanics is really the probability density. That really tells you the intensity of particles, how many particles are there, or what's the probability of finding a particle at any point in space of time is equal to minus gradient of whatever sits here is going to be your current density. Does that make sense? I mean, if you find the wave function and then you take d by dt of mod psi squared, and you can write it in this form, whatever is sitting here is your current density. Right? And so you can start from your time-dependent Schrödinger equation. You can write, IH bar d psi over dt is, Hamiltonian times psi. And from here, you right away you can see that, d psi over dt is Hamiltonian times psi over IH bar, right? Right. And you can take a complex conjugate of both sides. You get minus IH bar d psi star over dt is equal to Hamiltonian is, it has, complex conjugate of it is itself. It's a Hermitian operator, so it doesn't change. And you get a psi star here. So I think you can now see that you get d psi star over dt here is Hamiltonian psi star over minus IH bar, right? And you get this, you get that. And d, from here is equal to psi star d psi over dt minus, plus psi d psi star over dt. Makes sense, though, right? And you know this, right? You substitute it, and you end up with this. Right? So I'll ask you to do this. In fact, I'll ask you to do this in a slightly different way in the next assignment. This is the situation when you don't have a magnetic field. If you have a magnetic field, there is an extra term here, and that's also related to superconductivity and Meissner effect and some of this topological stuff we want to talk about later in this course. So if you have a magnetic field, it also has a term that looks like a magnetic vector potential times psi star psi. We're going to talk about that later. So, but this is the method of derivation at least. Okay? Just to be complete the story, discussion. This is your momentum operator in the absence of a magnetic field, which is minus IH bar d by dx, right? This is the momentum operator in the absence of a magnetic field. And I'm saying this now without derivation, but we are going to actually derive this whole thing later. If I have a magnetic field, the momentum operator changes. It changes to, where A is the vector potential, magnetic vector potential. It changes. So quantum mechanically, it changes to this vector potential term. Right? And we're going to Once you have this, you will have this extra term come out, you know, from this relation. So yeah, okay, yeah.
And in case where there's a magnetic field, you would just perturb your, you would just perturb the Schrödinger equation.
It's a good point. Actually, with just the static magnetic field, the Schrödinger equation is exactly solvable. You don't have to make any perturbation. You know, you can solve it exactly. And you see the electrons form what called Landau levels and all. We are going to see that. You know, because for a static magnetic field, it's exactly solvable. The problem starts when you have an electromagnetic wave, you know, where it's dynamic. You know, it's changing in time. You know. That becomes a little trickier. But the static is exactly solvable. You know.
But in that case, like again, you would just perturb the time Schrödinger equation.
You can find stationary states analytically for that. You know, you can solve this problem exactly. Is what I'm saying. Okay, yeah. So, all right. So this is the expression for the current flux of any quantum mechanical object, as long as you know its wave function. So you can just apply this and then find it. Yeah.
I mean, do you have an analog for like the n and v? I mean, for current is equal to the density times the velocity. Right?
Yes,
Do you have
yes.
like an analog for the
Right. So we're going to look at that now. It's a good question. So, you know, what's the analog of the flux where you break it up into velocity and density, right? So let's look at one example, and we okay. So we can let me give you an example for that. But before that, let me just say that for a large part of at least the first half of the course, we are going to start here, and then our whole mechanics of finding the total current will be the following. You start with the wave function, you apply this, find the flux, or you know, here's an example of a charge current. We multiplied it with the electron charge to find how many, you know, amps per centimeter square are flowing through a solid. Obviously, to find the wave functions, you must know things like band structure and all that. So that's understood. We'll develop some, you know, very simple models, like the 2x2 models of band structure, and then apply this and start doing calculations of current and all that. So to find the total current, we are going to, you know, there's a very well-defined procedure. If I put barriers, sometimes there is a tunneling and transmission. We're going to add that in. So essentially, it's all built around this picture, you know. And then go, you know, refine it more and more, and then finally end up with a kind of a more detailed expression. The reason for current flow in any solid is because you cause an imbalance, or, you know, with a voltage or something like that, and that is controlled by the Fermi-Dirac or occupation function. You know, so we're going to look at that, and the voltages and all will control these occupation functions. And for example, if you have a two-terminal device, there'll be a left contact, right contact, to different Fermi levels, and that's what will drive the current. You know. This is the driving force, and how exactly the current flows is determined by the quantum mechanics of it. You know, so this is a general scheme of things, right? We're going to start applying this to many cases. So going back to the question you asked about how might one look at, you know, n times v. You know, how does it break up like that, right? So let's look at a few examples. You know. For that, to answer that question. Okay. So the first example we had already started talking about it a little bit is a free electron, right? Just a free electron where potential is 0, right? The potential term is 0, or in other words, it's a flat potential. It's not changing in space. Right? It's a 1D potential, and for that you can solve the Schrödinger time independent Schrödinger equation exactly. You know, so that's your time independent Schrödinger. Vx is 0. So the wave function is just a superposition of a wave going to the right and one to the left. Right? K is 2 pi by wavelength that we talked, and the allowed momenta are continuous. H bar times K is the allowed momentum by de Broglie relation, and the energy is just this. We have talked about that. That's continuous, right? Now, if I have this mixed state of, you know, right going and left going state, right, partially right, how much? So if I measure this state once now, what is the probability with which I'll find this particle moving to the right if it is in this state? Do you have that feel? I mean, how, if its wave function is given by a times this plus b times that, what is the probability if I do a measurement of the state that I'll find it's actually moving to the right? Yeah, it's mod a squared. And probability is moving to the left is mod b squared. The sum of a squared and b squared is 1. This is what we mean by the amplitude of the wave function, right? This is the coefficient we were talking about earlier. Okay? So, okay, so as a result, this is not a real momentum eigenstate, but physically, quantum mechanics says that if I have a particle that's in that state, mixed state A and B, and if I do one measurement, if I just do one measurement, there is no such thing as probability. I'll find it either going to the right or to the left. I'll get only one result. Right? You can see, I mean, there's well, that's obvious, right? I will get either going to the right or to the left, right? But if I repeat that measurement a billion times, and I draw a histogram, how many times did I get right? That's mod A squared and that's mod B squared, right? That's what we mean by quantum mechanics. Right? That's the interpretation, at least. So, so that the momentum of, let's just look at the right going state. Momentum of the wave function part that's only going to the right. That's a e to the power, ikx. And the momentum is just h bar times k, which is the k sitting there, right? Because momentum operator acting on this, will do a do by dx. It will pull out this ik to the front and multiply by h bar, so you get h bar k. Right? So that's the momentum. Right? So momentum eigenstate. And now you can ask, can I look at the current of this state, right? I mean, by using this relation, right? So let's apply that relation and write down the current of, as an example, we are looking at this particular state here, right? This state, right? Unique k, so it has a unique wave function. It is a e to the power some ikx, and k is unique. So my current density is, or flux, if you might, is 1 over twice mass, right? And then I have to do this whole big operation. And I got psi star. What's psi star? Is a star e to the power minus ikx, right? So you can, I'm just writing this down all throughout. So you get a star e to the power minus ikx times the momentum operator acting on this state. What will I get? If momentum operator acts on this state, right? So you get, minus ih bar d by dx, right, of this whole thing, a e to the power ikx, right? You can see it will pull out ik to the front, and I times minus I is 1, so you get h bar k times psi. So that's a momentum eigenstate, right? So what you get here is just h bar k times a e to the power plus ikx. You see that, right? And similarly here, you get, a e to the power ikx, h bar k, e to the power minus ikx. Okay, so all that stuff, a star. Okay, so what you get in the end is mod a squared over twice mass, and you can see these things cancel for this particular state, and you get 2 times h bar k, right? Right? All right, so now mod a squared times h bar k over mass, right? That's what you end up getting, right? All right, so now you can look at this and say, what is h bar k over mass? That has a notion of the velocity, right? Has a notion of velocity, right? And what is mod a squared? Mod a squared is really 1 over the, rather, it's the normalization factor, right? So if I take mod psi squared dx, I get, just to be clear, an infinitely long thing is not normalizable, but mod a squared 1 over, so anyway, I'm going to say mod a squared has notion of the number of particles per unit volume or unit length. That's the same thing. This is not exactly normalizable. Free particle in infinite space is not normalizable. We know that. But if you put it on a finite space, then that is 1 over square root of length. So it's saying how many particles are there per unit length. That's n. Right? So this is the breakup of n and v, analogy to the classical picture here. Right? H bar k is the momentum or mass, and in a solid, in a crystal, periodic crystal, this will become the group velocity, slightly different from the free electron velocity and such things, and so on. But that's the general idea here. Yeah.
And you'll get a similar, you'll get a similar expression for every potential.
if I get a
It's like harmonic oscillator. You would still
good
have
question,
that.
very good question. Maybe let me ask that as a question to the class now. So that's a free electron, right? And let's look at the second problem. No, I'll look at the third in a second. Okay, here, a particle in a box or a harmonic oscillator, right? So let's say you have a particle in a box problem. We will talk about both particle in a box and especially the harmonic oscillator in greater detail in the class tomorrow. So let's look at the harmonic oscillator. It's as good as the particle in the box. So we are going to talk about it in detail tomorrow to develop this sort of creation annihilation formalism, because it's going to become important later in the course. But let's look at this. So here's the wave function. This is psi for the ground state of the harmonic oscillator, right? You can go through this whole process and find out what is the net current carried by this state, right? But I will say that before doing that, let's look at it and say that should there be any current, right, carried by this particle, right? And the answer is no, it's bound, right? It's not going, it's not carrying a net current in any direction, right? Therefore, the net current should be 0. And the moment you look at the wave function, you realize it's real. It has no imaginary component to it, right? So psi and psi star are exactly the same. So as a result, by definition, you can see this will be 0. So a bound state, this is going to be 0, right? The net current carried by it is 0. Right? So that's an important point. Now, okay, so I don't want to get into more details today, but you can create a state where when we say the net current is 0, actually that is very much true. It is 0 for this state. But classically, you can think of a ground state. What is the meaning of a ground state? You have a ball at the bottom of this valley, and you have rolled it up here, and it's kind of going back and forth, right? That's the classical picture of a ground state of of this harmonic oscillator. Now, if I'm sitting here at any point of time, I can see periodically that there is a current flowing to the right. There's a flux of particles flowing to the right, and then to the left, and then to the right, and so on, right? Does that make sense? I mean, classically, there is that thing that is going back and forth, going back and forth. And that part of it is given by fact that you can break this up into a j going to the right plus j going to the left. Now, that is not necessarily 0. You can have a current going to the right or going to the left. That, the sum is 0, but individually, they may not be 0. So that's the thing. And we are going to see that and use that again and again in this course, because actually we'll see that most things we are going to calculate current is we have to break it up into the right going and the left going, and then look at the difference between the total current. Okay, so but this is an important point, that if you have a real wave function, so bound states will have real wave functions, and the total current density will be 0 as a result. And that's the meaning of a bound state as well. Okay. But internally, it's not 0. There's equal and opposite in two directions. Okay, good. So we can stop here today, and I'll have office hours till 11:30 today in my office, and tomorrow we meet at 5 p.m. In the class. And your assignment due date is Monday, 5 p.m. All right, thank you.